Hello, team. I feel as though I'm live right now, and so let's just see if this works. So, um, hi everyone, I'm Mr. Dharma, and please just type in the chat when you can hear me, that'd be wonderful. Alright, so today I wanted to look at graphing trigonometric functions. So, here we go. Trigonometric functions. Alright, so trig functions. I'm going to look at two main trig functions. Okay. There's also the tan curve, but we're not going to look at the tan curve, and we're not going to look at any other interesting types of curves for now. Okay. These curves in physics have a special name, and they're called sinusoidal curves. Okay. Okay, even though this is a cosine curve, it's still a sinusoidal curve. Okay, the reason for this is it looks like this. I'm going to draw a really rough sketch, and then I'm going to take us over to Desmos to show you what it looks like. Curves that look like that, where they keep going forever and ever, and they go in both directions. Okay, so these are called trigonometric functions, but specifically these ones are sinusoidal. And so the sine looks like this, and the cosine looks pretty similar, but it starts out of phase. And so it kind of looks kind of off. I think my picture's quite bad, so I won't leave that there because some of you will think that's how it looks. I could try a little bit better, and here we go. That's more like what a cosine curve looks like, but just wait for me to draw one on Desmos. Okay, two curves, really cool, and they have some interesting properties. They're symmetric in interesting ways. The cosine curve, which is the green one, and the sine curve is the red one, they are symmetric in slightly different ways. And we're going to look at that in a little bit. But first off, let me write what the functions are. So this one's a sine curve, sine of x. And I'm going to put that in brackets. Okay, so sine of x, it's really, really simple. It starts at 0, goes up, then comes back down. Then goes down, and then comes back up. Okay, that's a sine curve. Okay, it can go on. It repeats. It's a periodic function, so it will keep going. But I'm not going to worry about that part just yet. And a cosine function is once again very similar, but it starts at the top, goes to the bottom, then comes back up to the top. Okay, that's how they look. And so these are the basic equations, and I want to look at how we can sort of change them around a bit. And so here's what I will write. F of x, I'm going to write a fairly complicated looking function, and then we're going to simplify it down. Okay. I'm going to just do the cosine. The cosine is going to be exactly the same, except instead of sine, I'm going to write cosine. So I'm not going to do that. But we have four key things. A is the amplitude. This is sort of like our scale factor. It's sort of like our K. Then we have B, which is the frequency. And then we have C, which is the horizontal shift. And then we have D, which is, sorry guys, I thought I pressed this, but it's not, obviously not worked. So D is the vertical shift. Okay? So unlike the parabolas, cubics, and stuff, there's a lot of elements happening here, and so this can get really, really confusing. So what I'm going to say is, let's model. I'm gonna try and focus on. Let's set C to 0 and D to 0. Okay, so let's not do any shifts, and then let's just look at how A and B function. So I'm going to rewrite it again. We've got f of x is equal to A sine B x. Okay, A sine bx. That's probably a model that we can probably work with a little bit better than the other ones. And so I kind of want to sort of see how they go. All right, so if A sine bx is our model, A tells you is the distance from the middle to the highest point. All right, so I'm going to draw my screen. Okay, and so if I drew that was a trig graph. A is this distance here. That distance there to that distance there. So if you know how tall that is, that's what your A was going to be. Can you guys just type something to let me know that you can hear me? But yeah, so A is that distance there. And then B is how many times this happens. Okay. And so that distance there we call the period. And use the letter T. And so B is 2 pi over T, which is where T is how long it takes to complete one revolution. And by revolution, I mean, so back into our graph. So we said sine starts here, goes up, goes down, and then goes back to here. And right here is when we start again, right? And so this distance here, this distance here is what we call the T, and then B is just 2 pi on that. Thank you, Daniel. Thank you, Monique. Thanks, Rosemary. All right. This is fantastic. So that's what T is. So depending on how I'm modeling, I will have an x-intercept here, an x-intercept here, and an x-intercept here. But if I have a T value, I have an x-intercept at 0, and I'll have an x-intercept at whatever the T value is, and I'll have one at half of whatever the T value is. And that's kind of useful. Right? Similarly, cosine is exactly the same. And I'm just going to draw the cosine curves right next to here, okay? But they're going to look a little different because they start at the top. This is really bad, I'm sorry. They start at the top and then go back to the top. And so A this time is still the same height, but it's there. And for the cosine curve, I'm hoping that changes color. And no, it didn't. So let's quickly just change the color on that one. Alright, so cosine curve starts here, goes down, goes back up. And that didn't change color either. I'm sorry, guys. And so the period is from here to here. From when it goes to the top, when it comes back to the top. And once again, there's two x-intercepts here that happen at strange times, and that might be really interesting for us to do. Okay, that's what they look like visually. Okay, and for those of you asking, if we go back to our original graph, this point here, this point here and this point here, their values are determined by C, comma, D, right? Okay, once again, C, comma, D. So whatever your C, comma, D are, everything will shift. But we typically might have C, comma, D being 0, 0, and that's really comfortable. But you know, it depends on what kind of thing you're modeling, because you'd probably move your model onto a picture so that C, comma, D is 0, 0. Okay. Now that you've got this, I'm going to go to Desmos and show you what these graphs look like and how they repeat. Are there any questions at the moment? Okay, so just fire away if you have any questions, and I'll just quickly try and find my Desmos. Okay. So guys, can you just let me know if you can see this? And if you can, that'd be wonderful. And if you can also tell me whether what I'm moving on here is also changing, that'd be great. Okay. So here is a sine curve, just one of them. And it starts at 0, goes all the way up to 1, goes back to 0, goes all the way down to -1, and all the way back up to 0. And that's very standard in a sine curve. Oh, fantastic. Thank you, Daniel. All right. So that's what a sine curve looks like. And this is one intercept, and this is the other intercept. And typically, the other intercept, so Monique, C and D typically is 0, 0. Vertical shift and horizontal shift, wherever the start is. Can you see that in this graph? I've got 0, 0 as C and D. So my equation for this one, if I were to draw it, yeah. Thank you, Rosemary. So if I'd write y equals, or f of x equals 1 sine 1 x, that's what it looked like. And you can see that I haven't got a C or a D because that's 1, 1. And so that's my model, and it goes. And if you can also see that this line not only goes this way, but goes forever that way also. And I think that's pretty useful. Okay, and I don't typically want to shift away from the origin for the first point, and so horizontal shift and vertical shift I try to keep as 0, 0. Just like in my parabolas and the other things that I've been working on, I typically keep one of the x-intercepts as 0. And then you're like, okay, Mr. Dharma, what's really exciting about this? Let's see if we can change this up a bit. So what I'm going to do is I'm going to call this A, and I'm going to call this, instead of B, I'm just going to write 2 pi over t, because I prefer using A and t. Yes, Monique, yeah. So we'll typically use 0, 0, unless you really change. Okay, this looks horrifying. Okay, but suppose I said A is 1, that's fine, and t, I want the whole thing to repeat every 8. Look at this. It starts at 0, 0, goes up, goes down, and goes back up, and finishes by 8. How cool is that? Just that equation, 2 variables that are, helping us out. A tells us what the highest point is. So if I changed A from 1 to 1.5, can you see that then the top point now is at 1.5? This distance here is 1.5. Can you see my mouse? Yes, you can. All right. So this distance here is 1.5, but the period is still 8. And so the b value, instead of using b, I'm using as 2 pi divided by t. Okay? Some people might like to write it like this, call it b, and then add a slider for b, and then go, this is a fixed value of 2 pi divided by whatever t is. And that works too, because it will still give you the same kind of thing. But I prefer to write 2 pi over t in that function, because it looks a little nicer, because this seems a little, bat. So that's kind of really important. And so depending on where I want this point, I would type a t. But sort of like a parabola, if I wanted this curve, and this is what I'm modeling, then t is going to be double where the other x-intercept is. And that's going to be useful for me. So if I wanted an x-intercept at 0 and another one at 6, and it to go up like this, I'd go, what's 2 times 6? That's 12. And I'd set c to 12. And watch that. And it goes down at 6. Ain't that cool? And so you can always do that. And that's a really cool way of modeling. Some of you will notice other ways of doing it, but that's, irrelevant. T, for me, is really important is the whole period, and you can change it how you want. Okay? That's the sine curve. And I'm just going to quickly show you the cosine curve. The cosine curve, the standard cosine curve, starts at 1, goes down to 0, goes down to -1, and then comes back up to 1. And so if I were to write a cosine curve out, f of x equals a cosine b of x, I'd once again want to change b to 2 pi divided by t, right? Because t is really important to me. And so t, for me, if I once again set it to 8, watch what happens. The period is 8. It starts, okay, I'm going to get rid of this one, sorry. It starts at 0 and goes down at 4 and comes back up at 8. But you can sort of see like a parabola looking thing down here. It's not quite a parabola, but once again, a cosine curve goes backwards and forwards quite a lot. And so that's how these trig models are. And so if I wanted to model something, well, here's what I might do. So I'm going to draw a curve. You guys can see what it is, but it doesn't matter. I'm going to draw a curve, and I'm going to call this x squared. It doesn't matter. You don't need to worry about this part. x squared negative x squared plus 3x. Yep, and that's what I'm going to model. And you're like, Mr. Dharma, that looks pretty gnarly. And I was like, yep. So I'm just going to go change this up a little bit. Nope, that's the wrong thing. Just change the y values. Sorry, guys. -3 to 3. Okay, so let's have a look at this. I have this weird looking parabola, and I want to model it with a sine curve or a cosine curve. I'll go, well, I know that my model, okay, I'm going to just put a domain on this. I'm going to say from 0 to 3. Okay, so I want to model that shape, okay, and I'm going to actually just hide the equation of this in there so that you're not too worried about it. Okay, so alright, so I want to model this. So I'm going to use a sine. I'm going to go f of x is equal to a sine b of x. Okay, and we'll make some sliders and let's see if we can match this to this. First thing I want to know is what's the tallest point? The tallest point is 2.25. So I'm going to set a to 2.25. And look, it's just as high. This is great. And then I want to know, what's this point here? That's at 3. And so if a sine curve goes up, down, then up, what do I want the period to be? Well, I know that b is going to be 2 pi on t. And so what do I want t to be? Okay, what do I want t to be? Well, I want t, sorry, that looks really ugly. I want the period to be twice that, so it's going to be 6. And look at that. Can you see this purple line is very close to that blue line? And I think, is it possible to make this cosine graph as the same as a sine graph by shifting C and D? Yes, in fact, Zetong, yes you can. And so cosine and sine are very similar, and they're actually just a shift, and that's probably why we'll typically use a sine curve more often than a cosine curve. And when you come into level 3, you'll have to do some practice of converting between cosines and sines. But great question. But look at this. I've modeled a really close sine curve to this blue parabola that I had. And I think that's pretty cool. I'm going to actually just change the color of this one so you can actually kind of see it a little bit. I'm going to change it to red. No, I don't know if that helps. Can you see how that blue and that red are very similar? And so that's what I might be doing. As long as you know what T and what A are, you'll be able to model very well. Okay? And so if I wanted to, model a cosine curve over something, it's really important that I might, I don't know, I'll do a cosine curve. So I'll just change my equation here. Don't worry about what it is. Okay, suppose my cosine curve is this. Right, let's try and model a cosine curve to this. Right, what do I know? Sorry, I'm just going to go negative. Okay, so let's try model that blue thing here. Well, since it's at the top, at the start, I know instead of using a sine curve, I'm going to use a cosine curve. So I'm going to leave all this, and I'm just going to change this word from sine to cosine. Okay, I've got to spell that right. And first off, I want to know the height, and this height is, A is only 2. Okay, and then I want to know, well, what's the distance between these two? Because that, if I times it by 2, should be my total distance. And so that's 1.141 plus 1.141, so that's 2.848 or 828, and then I want to double that, and that's going to be my t value. So it's going to be 2.828 times 2. Okay, if you do some quick maths, it's 5.656, so I'm just going to write 5.656, and look at that. Isn't that a really cool model? I know it's really bad here, like look at how terrible it is here, but look at how nice it is up here. And so that's why that might be something that you end up modeling, and you might go, oh look, my cosine curve looks really nice. Okay, but it's all about playing around a little bit. These numbers don't have to be accurate. Okay, and so I'll leave it to you and your teachers to go over how we model these a little bit more accurately and have a play around, but these are the two functions, the sine function and the cosine function. A is the height from the bottom of the graph, the middle of the graph to the top, and B tells you the frequency, but T is the real thing, is the period. How long does it take to do one cycle? For us, the one cycle is from 2, takes us 5.656. Okay, that takes 5.656 units, seconds, I don't know what you want to call it, to do one cycle. And that's going to be useful to us because that's going to be the distance, or double the distance, between these two intercept points. And I think that's really, really important for us. Okay, are there any questions? I'm going to just switch back to my whiteboard, and just in case there are any questions, please sing out. Okay, I'm just going to wait a second or two, and then I'll call it a day, because I think that's all I wanted to cover. Is b always 2 pi over t? Pi is spelt with just pi, there is no e, and yes, b is always 2 pi over t, as long as t is the period, right? How long it takes to complete one revolution. Okay, so one revolution is really important to us. One cycle of the sine functions. Sine function. See, this is one revolution. So t is always that distance. Okay, and here, once again, one revolution. T is always here, and 2 pi over t is equal to b. And the reason for that is because the standard period is 2 pi. But we'll get more into that next year in level 3 calculus. Are there any other questions? Is there like a practice question to do? I think your teachers will give you some questions to do. You're more than welcome to just quickly look at the trigonometry section in your book, and your teachers will give you some things to model. I think it's quite important that you just maybe look at some Desmos tasks. There's the Desmos marble slides trigonometry task that your teacher probably will assign to you, and that's quite useful to have a check as to see how this works. I don't want to give you a practice task on this call because it's going to be harder for me to check, but your teacher will be able to do this. How do you know when to use a sine or a cosine? Well, typically you'd use a sine curve if it starts. You'd use a sine curve when it starts at the middle and goes up, then goes down, then goes down, then goes back up. And you'd use a cosine curve if it starts at the top. And so that's going to take a little bit of intuition. So this one here is the cosine because it starts at the top, goes to the bottom, then goes back to the top. But remember, this is just me restricting the domain. but these functions just keep on going and going. And so depending on what's happening at the origin is what's going to determine what kind of function you're going to use. Okay. Sorry, I just realized I didn't change slide, so you can't see me waving my hands around. So once again, a sine curve starts at the middle, goes up, down to the bottom, and then back to the middle. And that's when you'd use a sine curve, and a cosine curve starts at the top. So depending on what kind of model you're modeling, you might want to use a sine or a cosine. But as Zitong said way early, depending on shifts in C, you could probably use either. But typically we're going to probably use C and D as 0, 0 because you want to model a model quite accurately, and so you want to put it on the graph, and you have the interesting parts at 0, 0 or at 1, 0 or something like that. But you can discuss that with your teacher. Is that clear? All right, team. I'm not going to do much more. I'm going to call it a day there. Once again, another 30-minute video. Hopefully you found that somewhat useful, and just check what your teachers put up for you to do. Okay? Stay calm, stay happy, stay safe. We have just finished 6 weeks of lockdown. So well done. Awesome stuff, team. I'll catch you later. Bye for now.